Maria is one of the newest faculty members of the Robotics Institute. Maria is an architect, a researcher, and an artist working in the field of computational design and digital fabrication. Her work lies right at the intersection of architecture and robotics. She produces spaces and robotic systems that can construct themselves and change in real time. She has been commissioned and exhibited by institutions including the Milan Design Week, Ars Electronica, Capelica Gallery, the Cooper Union. And in her research, she has also been collaborating internationally with institutions such as the Autodesk Pier 9 in San Francisco, ETH Zurich, WeWork in New York, and Bartlett School of Architecture in London. In January 2020, so just this year, Maria started as an assistant professor with the John H. Daniels Faculty of Architecture, Landscape, and Design at the University of Toronto, and she joined the Robotics Institute this fall as a new faculty member. Maria holds a Bachelor in Architecture and a Master of Science in Computational Design. Before joining UofT, she was a research associate and doctoral candidate at the Institute for Computational Design and Construction at the Faculty of Architecture, University of Stuttgart, Germany. So without further ado, join me in welcoming Maria to the UofT Robotics Institute as a new member, and join us and listen to her keynote on task and site-specific robots for architecture. Do smaller robots equal larger architectures? I am looking forward to your talk, Maria.
Thank you so much, Jessica, for both the invitation and the lovely introduction. Hello, everyone. It's very nice to meet you all. It's also amazing to have this opportunity to present my work alongside with all of the work that we've seen earlier today. I have to say that all of the presentations that I've seen and generally the event has really made my day, if not my week. It's been amazing to see all of the impressive and very diverse work. Well done, everyone, and congratulations. And of course, a special thank you for all the robot jokes. I've also written all of them down and now know how to entertain my students when I need to convince them that robotics is cool and is a thing in architecture, which sometimes needs to happen. So my name is Maria, and as Jessica has mentioned, I'm an assistant professor at the Daniels Faculty of Architecture, Landscape, and Design here at the University of Toronto. I'm an architect and a researcher. I'm also an artist and a roboticist. I'm wearing a lot of hats all the time and having kind of multiple personalities because of that, which is both fun and sometimes, can be tricky. But I'm always very excited to present my work to the community of roboticists outside of the world of architecture. And that is also why I'm going to start my presentation with a little bit of kind of history overview and generally giving you an introduction into what is the relationship between machine design and robotics design and architectural practice. And of course, this relationship is not entirely new and over the time has taken many, many forms, starting from speculative visions of architectural futures, wherein the boundary between the architectural space and the machine itself is blurred, to prototypes of intelligent buildings that are capable of not only mechanic movement, but also intelligent response, decision-making, and even boredom in some cases, to, of course, the construction automation boom, where conventional construction and fabrication processes are automated and are performed by teleoperated or in some cases, fully autonomous vehicles. The relationship between the machine or a robot, depending on which language you choose to use, and the designer and design practice, as we have been observing it in architecture over the past almost 20 years, has become almost synchronous with an industrial robotic arm that is performing complex and oftentimes meticulously choreographed movement by placing, assembling, extruding, cutting, and winding materials. Within this lineage of research focusing on the appropriation of robotic technology, primarily appropriation of robots from the manufacturing line context that it was, of course, initially designed for, the community of computational architects and computational designers have authored a myriad of processes, material systems, and effectors and custom tools. However, we are still finding ourselves inherently constrained by the industrial robot's body itself. The robot that applies not only scale and reach limitations, but also adoption of installation and integration protocols, workflows, routines, software and hardware control tools and environments, and of course, certain accessibility limitations that come from the cost of these machines. In contrast to this appropriation of technology model, if we sidetrack away from the physical machines and for a second look at the history and current state of computational techniques, specifically CAD, it is evident that the community of researchers in computational design, digital fabrication, and architecture have been not only leveraging available computational tools and techniques, but have also actively participated in the steering and development of computational tools for design, from early precedents in CAD software to contemporary developments of generative design systems that are gaining more and more tractions over the past few years. So within this context, what I suggest with my work is that we rethink our relationship with robotic hardware away from the established model of consumers and oftentimes hackers of available technology towards rather developers, and if not developers, at least active participants in the development of hardware. I call this shift, or the practice that emerges from this shift, designing with machines, a practice that is arguing for a design process that includes hardware, software, and architectural design, all of those as interdependent variables throughout the development of a piece or throughout the development of a project. My personal journey into designing with machines and designing the machines themselves, somewhat not entirely intuitively, started with spiders. Specifically, it started with a small research project on spider webs that I was lucky to be a part of back in my first year of grad school. And the project was focusing on the web building sequence of certain species of house spiders. I'm not really going to go into the project and into the research, but the two key points that are important for me still in my work are the complexity of the built object that emerges from a set of behaviors that the spider performs. So the spider does not really have a plan or a section as an architect would, but rather performs these very simple choreographed movements using, relying on two inputs. And the two inputs are, of course, site geometry. So depending on where the web is built, the geometry of the web will change. And of course, the geometry of the spider's body, because it inherently depends on its own reach, on its speed, and how the body can navigate through space and change and manipulate material. And the second factor that got me really excited about robots looking at the spiders is the fact that a very small creature, or a relatively small creature, is able to produce structures that are way larger than its own body. So the relationship between the affordances of the material and the machine, which in this case, I say machine, I mean the spider or the spider's body itself, really creates this symbiosis where all of the affordances of both the material and the body are really leveraged towards the final structure that is not only very efficient for what the spider is doing, but also pretty stunning in terms of its aesthetics. At least that's how I feel about spiders. So being inspired by that, I've started maybe partially naively, partially very enthusiastically building my own devices and my own mobile robots, setting a goal to create fabrication systems that will create structures in a similar way to what Spider does. And an important aim for me here was to create a robotic system that can not only fabricate structures, but also can fabricate these structures in already existing environments of human habitats, which are already present in our architectural context. So not necessarily building from scratch, which is maybe how a lot of us imagine architecture. You know, you show up, there's an empty plot, you build a beautiful building and everybody loves you. I'm way more interested in looking into spaces that are already there, that are maybe not used or are not used in the way they could be used, that we can enter with our robotic systems and either adjust or recalibrate or add a new layer of both architecture, function, and meaning through these robotic systems. So the first machine in a series of machines that I've been building ever since is a wall climbing filament winding robot that consists of three kind of primary parts. The first part is a central vacuum assembly that allows the robot to actually stay on the wall. You can think about it as a vacuum cleaner that is scaling the wall. Then, of course, there's the wheel assembly that allows it to move around, and an end effector assembly that allows it to handle the material and attach it to predefined anchors. The robot has two control modes. One is autonomous, where it is relying on an external perception system in order to know where it is and where it's going. And the other one is manual for troubleshooting and kind of fixing mistakes as they arise, which, as I'm sure all of us who are doing robotics know, happens more often than we want it to. Two robots of the same type can interact with each other by passing this little cartridge of material from one machine to the other. Each robot sits on a wall and they meet at a corner between the two walls. And each robot is also able of attaching the material to predefined anchors in the space by actuating this little winding end effector and wrapping the filament around the anchor. So this is roughly what the system looks like in its entirety. So as you can see, it's not only the robots, but it's also a couple of laptops and some web cameras. The system since then has been slightly upgraded, but it is important to note that the robots are not, that the computation is not happening on board, but there's a server that is actually getting the information from the cameras and is dispatching the commands. So this is what a single iteration of a fabrication sequence looks like, or rather a sequence of operations that the two robots need to perform in order to lay a single strand of filament between two walls. There's a whole bunch of routines that are happening. There's a approach, anchor, path find, pass, and then again, path find, approach, anchor. And through repetition of these routines, the fabrication process is actually conducted. So here we can see the two robots actually producing an architectural object, again, in situ in an existing interior space that I was very lucky to have access to during my studies back in Stuttgart, which was a whole other research project of how do you get space in order to deploy wall climbing robots that are way too loud to co-occupy any space with humans. But generally through repeating all of these reasonably simple routines and passing the filament from one to another and continuing to anchor, they can create a pretty complex set of three-dimensional shapes that are not only interesting in themselves, but also have a certain human scale. Of course, this is maybe arguably not really architectural, but rather furniture scale at this point. But this project became an important proving point for myself and maybe even our field that an architectural robot or an architectural fabrication robot does not mean a robot arm. It can be something that is small, something that is reasonably cheap and very transportable. But in my goal of getting rid of the limitations that I was so used to in the robotic arm, I arguably got myself into a whole new set of limitations by developing these robots. And I guess since today is the pun day, the pun would be that I got myself into a corner of limitations. Nobody ever laughs at that joke when I make it in lectures. So I think that's fine. But anyhow, this new corner of limitations was, of course, defined by how the two robots, yes, thank you, how the two robots pass this bobbin of material between each other. So in order to fully operate in order for two robots to operate together, they need that 90-degree corner, which of course is not always the case. Different sites have different geometries and different parameters. And something that I was really interested in exploring is what happens if my anchoring walls or my formwork for whatever I'm building is not actually a corner, but rather two surfaces that are at a distance from each other. So the first idea was to get another robot to come and help out. And this is where I've developed an incredibly highly technical end effector that I call a robot spatula that allows one robot to pick up another robot and then pass it from one wall to the other. So together, these two machines, and as you can see, I only have one climber in this particular test. Together, the two machines can perform a wider range of operations within a wider range of site scenarios, following the same logic and the same sequence as in the first project. And kind of thinking about these multi-robot collaborations, I was very fortunate to be offered to have to show a piece at the Milan Design Week. And the project was, of course, a big step in upscaling the existing system. And one of the big and interesting challenges here was I basically arrived at the exhibition site, which is kind of how I start every project. I show up on site and then figure out what my robotic system needs to look like. So the site had these two reasonably large walls positioned at a distance of 7.5 meters from each other. And of course, the question is, how do you span this gap of 7.5 meters between the two robots or between the two walls? And the solution came to me somewhat intuitively because there is all of this space. Of course, I can't really have a robot arm. I was worried that if I have a robot on the floor, it will really intervene with the exhibition visitors walking through the space. So I've developed a new iteration of this cooperative kind of robotic team member, which is basically a single axis robot that travels on a piece of rope and carries the bobbin of filament between the two wall climbers that have largely remained the same with minor upgrades. So again, this robot is now performing kind of a role of a mediator between the two wall climbers by performing the passing routines. There are some upgrades that I'm not really going to go into on the communication side. And here you can see a short video of what the actual process looked like. So the wall climber meets the thread walker or the shuttle. The passing routine happens with these electropermanent magnets. And then the routine pretty much remains the same. The wall climber continues anchoring the material to pre-installed anchors. The anchors are installed by humans. We're still working on that part. And then through iterations of this passing, anchoring, and passing, we can create a pretty large structure. And what is most interesting for me with this project, and I think also where I kind of realized how much potential one can have when deploying teams of not only multiple machines, but really teams of very diverse machine bodies, is how both of these robots, both the shuttle and the wall climber, are very simple 1- and 2-axis machines. So if you think about them as individual robots, they may be not as useful. But the moment you combine them into this team and the moment the passing routine is introduced, the workspace between this linear, like a single axis line of the shuttle and the 2D plane of the wall climber, the whole volume between the two planes suddenly becomes the work envelope for the overall system. And I got really interested in how to strategically think about very simple and minimal robots, but then leverage their abilities through this combination of multiple work envelopes and kind of stacking or linking multiple work envelopes into the work envelopes that would, do the things that I wanted them to do. So here's kind of a brief diagram of that, where we have, again, two planes, a single axis shuttle, and once they're combined, the whole volume in between the two planes is rendered as a fabrication work envelope. And of course, this project further demonstrates, again, this question of scale, how small can a machine be, and at the same time, how large can the fabricated object be. The next project that I did following this one largely, again, reflected on the previous work and looked into limitations that were discovered as the work was developed. And there were two really big issues in the previous project. One was time, because it took quite a lot of time to actually fabricate this large structure, partially because each of the wall climbers spends more than half of its operation time simply sitting there waiting for the other two team members to finish their routines. So there's a lot of idle time. There's a lot of kind of energy and time wasted by each machine. So addressing that question seemed pretty intuitive by simply adding another shuttle robot so they can work in parallel. So each of the wall climbers is actively performing fabrication routines. And then the second question was the problem of power, because all of the previous robots were, or at least the wall climber robots were, powered through a cable. So they're tethered robots. And the reason for that is that the vacuum pump that I was using in order to make sure that the robot stays on the wall eat up quite a lot of energy. So a battery wasn't really feasible at the time. So I've rethought the whole wall climbing strategy and started to think about different other types of architectural materials that are beyond walls, or architectural materials and also architectural topologies that are quite common in our living spaces that I could also leverage as climbing material. So I developed this robot that I call a sandwich bot, which basically clamps onto a thin sheet of material using a series of magnets that are installed both in the robot body and in the treads. And once the robot is clamped, it can safely move around in this case, it's a transparent sheet of plastic, but by calibrating the magnets, one can use it on thicker and thinner surfaces. There's a prototype that I've done after this project on an actual insulated, like 4-layer insulated glass, and that also works. And what's really nice about this robot, of course, is that once it's not moving anymore, it's not wasting any energy to remain attached to the surface. So overall system for this project consisted of these two suspended sheets that were installed in the exhibition space, a set of 2 sandwich robots, a set of 2 shuttle robots, and an external perception system. And in this case, I switched to the HTC Vive perception system in order to kind of eliminate some of the tolerance issues that I had in the previous work. And what was interesting with the perception system here, because I was using these double layered robots, I could actually have my localization markers on the outside of the work envelope. So the localization marker is installed on the passive side of a sheet climbing robot. So there's no obstruction of the marker that is happening throughout the fabrication process, which was largely a problem in the two previous projects, because as you create more of the filament structure, filament begins to obstruct the visual markers. So again, the overall system looked somewhat like this. And again, one of the parts that is most exciting for me is this linking of very minimal work envelopes in order to achieve larger volumetric work envelopes where there's a lot of design space that is possible through it. Another interesting thing with this robot was that I could afford to eliminate the whole winding end effector, and that was also a function of getting rid of the tethered power supply. So the whole anchoring routine was rethought into kind of a subroutine of a locomotion. So the robot simply drives around an anchor, and the thread or the rope in this case is then attached to it, and then it continues to pass the filament cartridge to the other robot and continue the fabrication process. So this is roughly what the whole fabrication process looked like. Again, it was a collaboration of 4 machines making a sculptural object together. And both this and the previous projects were demonstrated, not only shown in an exhibition context, but also partially fabricated in an exhibition context. So we started setting up the robotic system a few weeks prior to the exhibition opening, and then fabricated most of the object during that preparation time, but we intentionally left some of the object unfinished in order to actually fabricate it during the exhibition to really demonstrate not only the robotic system, not only the artifact of the robotic system, but really to demonstrate the process and kind of have the audience engage with these types of fabrication devices and see how people respond to them, how people react. With the previous project, we even had a couple of sessions where we let people drive the robots from the pendant. Something that I have learned is don't ever let people drive robots during the happy hour at the exhibition opening, because, drinking and driving is a no-no, even if we're talking about tiny robots. Anyhow, what is also interesting about both of these projects is how, and what is kind of over time has become one of my points of fascination with this work in custom hardware development, is that as a designer, I approach most problems first from the design perspective. So I enter the exhibition space, so I enter the site. I think about different possibilities of what could be made within the site. And then I start thinking about what types of robotic systems I would need to develop in order to make that happen. And then there's this interesting moment where kind of my architect hat wearing persona and my roboticist hat wearing persona are having this little, not necessarily a fight, but rather a negotiation between basically the feasibility parameters. So I'm continuously optimizing my hardware to get to the design results that I want. But then also as a designer, I'm continuously adapting to whatever is feasible from the hardware perspective. And I think that is a very interesting way to think about development of robotic technology when it deals with the design world and design profession. And where I would like to take that further is, of course, into a more interdisciplinary institutional structure where it's not me wearing 2 hats, but rather a larger team of people from different disciplines coming together at the earliest stage of project developments, rather than later when the project is already somewhat defined, either on one side or the other. So another project I wanted to show you today is slightly different from the other 2, not necessarily in the way it's conceived, but maybe in the way it looks and in the way a robotic system works. So this project, just like the other 2, really started with the site. And the site here was a bit tricky. Again, I was invited to do a show by this gallery in Slovenia. I showed up and realized that while the gallery looked, like a pretty normal room from the images, the actual structure of the gallery, so there are basically no solid walls in the space. There's a row of columns on one side, and then there's a row of columns on the other side that are boarded up to pretend to be a wall, but there's you cannot anchor to that. So it's like, okay, you have no walls. I have a bunch of wall climbing robots. This does not sound very good. So the first idea, and kind of the idea that I ended up running with, was to create a new substructure within this existing space that would be designed in a way that it is flexible enough to be tailored. If you think about tailoring in a kind of traditional textile practice way, tailored to a space in a very flexible manner. So it's a system that allows you a certain level of precision in terms of robotic positioning and operation, but also it allows you to just show up on site and install it and deal with all of the on-site tolerances as you go. Because of course, we think about buildings as rectangular spaces, but they never actually are. There's a whole bunch of tolerances that come from the way buildings are built, how old the building is, etc. So I've created this frame that basically consists of aluminum rails and a very flexible rail that is a rack and pinion track for the robots that I've made. And the rails were fabricated in such a way that they basically rely on the flexibility in the rack and in the rail plastic material, so that you can really adapt the rail to the geometry that you get on site. So you don't have to worry about the geometry being off, a little bit off from the drawings that you maybe received beforehand. So the locomotion rails were fabricated with this flexible, lightweight plastic and some aluminum rails. And the robotic system itself, the fun part, consisted of 3 machines of 2 types. The 2 filament handlers that were traveling along the vertical parts of the rail system, and a small filament shuttle, again, in terms of logic, it's very similar to the previous project, but in terms of locomotion system and how the whole fabrication team operated, slightly different. So the robot that sits on the floor on the rail, the shuttle robot, is passing the material from one machine to the other, while the vertical ones actually go up and anchor the material to the anchors. So this is roughly what the shuttle robot looked like. It has, again, it's a single axis machine that has two motors in it, so it can pivot this end effector and it can extend a little hook in order to grasp the loop of filament. And then the handler is also a 1-axis machine that has a single actuator that allows it to actually perform the anchoring routine around the pre-installed anchors. So this is what the overall anchoring, passing routine looked like. And again, similar to previous work, through performing these anchoring and passing operations over and over again, the 3 robots can actually achieve a result that is not only kind of interesting, but also architecturally becoming relevant. A small detail about the vertical robot, it's actually not really a vertical robot, even though I call it that way, but it also operates on the horizontal part of the frame that actually allows you to create not just an arrangement between the 2 columns, but a properly enveloping space filament wound object that exists within this gallery. So the overall structure looked somewhat like this. By iteratively performing the routines, the robots were able to fabricate the filament wound object that was not only defined by the robots themselves, but also really defined by the boundaries of the available space. And this becomes interesting from the design perspective, where when we talk about architecture, we often talk about site-specific processes. And here our site is the architecture itself. And then within that, by analyzing what the site can give us and what the robotic system can give us, we can really create structures where the design really relies on those 2 parameters. And again, talking about the work envelopes, we can see that the individual work envelopes of each robot are very minimal. It's basically the single rail that goes around the space. But once they're combined, the work envelope of the overall robotic system is enough to actually fabricate a pretty large structure and kind of a substantial structure. The fabricated object itself, in this case, the design process for the winding syntax, so the winding syntax is the sequence in which the points are connected, was a little bit trickier than in the previous iterations, because there the way the robots were interacting with each other was pretty straightforward. So in the first project, you basically create cylinders and then offset them for every iteration of the winding syntax in order to create the double curved shape. Here, because the robots were again tethered, and also because they are only a single axis robot, the there were a lot of limitations in terms of how these multiple surfaces that the robots were creating could and could not overlap. So for instance, when two surfaces are intersecting, if the intersection line is not an ellipse, then that intersection would be considered unfeasible and the robots would not be able to fabricate it. So there was a separate design tool that was developed in order to be able to actually play with the system. So before the system was really deployed in the space, a design tool was used in order to predict which fabrication sequences were feasible or not, and actually allow myself and my students to kind of play with the available design space as designers and think about different sequences that we could actually deploy here. Again, the design process for the overall project was really interesting from the perspective of having to simultaneously consider the site, the architectural implications of the result, and the actual design of the hardware system, along with the design of the software control and the sequencing. So first you have to have the robot body, then you have to figure out what the choreography of passing and anchoring is, and then it doesn't work. So you have to go back to the robot body, and then you kind of forget that you're on a rail, and then the rail comes back in. And this obviously somewhat chaotic process, again, is something that I find to be very interesting, where you have to continuously negotiate between these designer and roboticist parameters and kind of consider them within the same design process in these sequences of iterative design loops. A little bit about the surface intersections here that I've already mentioned. We've had to create a huge catalog of possible surface intersections and then have to go through them in order to actually define what were the successful designs, both in terms of their aesthetics and in terms of their robotic feasibility and speed of fabrication. But what is interesting, even though we've done all of this preparation work, at some point through doing this preparation work, we've also built a certain level of intuition of which types of configurations would work and which types of configurations would not work. So in the end, when we were preparing for the exhibition opening, and both during the prefabrication on site and during the exhibition opening, as you see here, during the exhibition opening, we're continuing to run the fabrication system, again, because I personally strongly believe that it's important to demonstrate these systems not just as artifacts, but as actively performing robotic systems. So while we were doing all of these performative fabrication pieces, we basically started to figure out new layers for the structure as we went. And that was kind of a fascinating realization. It's like, oh, we clearly needed to do all of the simulation, but in doing so, and then in practicing on site and in fabricating on site over time, we've also developed a certain understanding of which parts will work well and which won't. And that allowed us to, again, kind of step into this designer space where we could intuitively plan and intuitively change our plans as we went and as we continued to add layers to the fabrication system. And of course, what I think is interesting when thinking about this designer intuition is the ability to potentially change the fabrication process halfway through, or even develop fabrication processes that have no real ending. So that the fabrication process that continues to run in a loop, and then the goal is not necessarily the object or the artifact, but rather the choreography of change that the robots produce as they're winding, maybe unwinding, and winding a new system all over again. And then on the other hand, there's, of course, an interesting relationship between all the different parameters within the project. And on one hand, again, those are design parameters such as, the size and density of the fabricated object itself. And on the other hand, those are the technical parameters, like what is the motor torque of each of the motors, and what is the, payload of each robot. And then depending on the payload, what is the size of the material bobbin. And the schematic really demonstrates how every single parameter within the system is dependent on all the others. So the moment you change the resolution of the anchors along the rail, everything else in the system has to adapt. And on one side, one can argue that that is not a very practical system because it is only good for this particular task. But I would argue that it is a really practical design exploration, because these types of systems really allow us to think outside of the box of what existing hardware allows us to do, and potentially innovate both in robotics and in architecture and in material systems, and even in ways we occupy our spaces. So the presented robotic system and all of the presented projects outline, at least in my opinion, outline the affordances of this designing with machine methodology that I propose with my work. Co-design and co-development of a robotic system and the material manipulation and fabrication strategy allow to leverage on-site properties and allow to fabricate large-scale objects directly in situ using only small-scale and low-payload machines. Moreover, it of course offers an opportunity to consider these systems beyond fabrication and towards possible reconfigurable architecture applications where spaces continuously adapt either to themselves or adapt to their users. And ultimately, where I would like this work to go in the future, I would of course like this for this family of robots to grow. I'm not opposed to off-the-shelf robots. I think we need to bring off-the-shelf robots into this larger economy of custom, task-specific, site-specific, and generic and universal machines that could potentially collaborate and contribute the unique skills to a larger process, while also relying on their collaborators, on their robotic collaborators, to fill in the gaps where they cannot necessarily reach or achieve certain things. And I'm of course hoping that the taxonomy of these robotic species will grow not only in my work, but also through the work of my students and my collaborators. I think that a large part of my work is to encourage more interdisciplinary work between architects and roboticists, between architects and humanities people, between, you know, pretty much everyone who is involved in the development of these types of processes. And I'm hoping that this interdependency and kind of interweaving, if you will allow me another pun, of multiple different disciplines can really allow us to achieve design processes and development processes where we can consider software development, hardware development, architectural development, design development as all parts of a single continuous loop, rather than kind of outsourced parts that all belong to different parties. And again, what I would like to see in our field is kind of sitting down together with an empty sheet of paper and starting a project from scratch, rather than a model that I often see where, especially in architecture, where an architect would approach a roboticist or a computer scientist with a question, and then the question would not really be interesting for the other party. So I think we need to start working together at an earlier stage. And that is where I'm going to wrap up this talk. Thank you very much.
Thank you, Maria. That was a super inspirational talk. I'm sure the audience shares my impression. It's a pleasure to listen and see all the great work you have been doing. It's truly inspiring. I'm so glad that you joined UofT and that you're now part of the Robotics Institute. I can't wait to sit there and build something from scratch, honestly. I'm sure there are questions from the audience. So please, everyone, make use of the raise hand options in the participants window. You should see a little raise hands icon there. And then I'm going to call you and you can ask your question. The first question is going to come from Sefer Samavi. Unmute yourself.
Hi, thanks for the talk. I was just wondering, in these kind of sculpture designs, how much of the decision-making is done autonomously? And in general, I'm curious to hear your opinion on kind of whether autonomous decision-making even constitutes art.
I think, well, in my work, there is very little autonomous decision-making, and that has to do not necessarily with the fact that I'm opposed to it, but, you know, I am kind of a one-person show, and I have to focus on my hardware stuff. And that's also the part that makes me most happy, like developing the actual mechanisms and figuring out how to make everything work together. But there's definitely a level of simulation that is involved in evaluating different designs. I definitely depend on some autonomous processes in order to figure out what a design is, but also in like a full disclosure mode, I put a lot of effort into the design of the system and the design, like both the system in terms of the fabrication system. So how do you arrange material to achieve an X variety of shapes? But then when I get to the point when it's time to fabricate the final shape, I'm like, the opening is tomorrow. We should probably just make something. Which is, I'm also totally okay with. But generally, I think that autonomous processes are, of course, part of any, or can be part of a creative practice. There's a whole bunch of artists out there who are working with AI, and the results are absolutely stunning and way outside of what I could imagine myself doing. But yeah, no, I think just like with photography back when it was new, there was a lot of criticism that like, oh no, photography is going to kill painting. I don't think that's a valid argument. I think we should explore technology and figure out how to make it work for us in our creative practices.
There's some questions in the chat that I'm just going to read out for you, Maria. Mm-hmm. The first question is from Shane Saunderson. He's asking, when you approach a new project, how do you balance the desire to learn and explore something new against the time, ease, and cheapness of using solutions you know?
That's an excellent question that I don't have a good answer for. I think, I'm trying to really properly think about how I do that. Part of it is kind of working from intuition. I mean, of course, a lot of it is assessing the feasibility of every single step. But I'm also the kind of person who tends to take really big risks, which so far has worked okay for me. The cheapness is a big factor, but I guess due to the scale of the stuff that I make, I'm always I find that in terms of funding, my work is probably easier than a lot of the robotic arm work. But yeah, it's like a perpetual fight against time and a perpetual fight against one's own ambition, and kind of at some point in the project having to be like, okay, we're going to stop here. We're not going to develop a third, fourth, fifth robot. Because there's always, of course, a bit like for every project, there's a way bigger plan that doesn't get shown in lectures. But at some point, you have to start cutting down on the ambition.
Another question is from Adam Hall. He's asking, do you consider the construction of your sculptures a performance art on top of the resultant structure?
Also a great question. I think with my work up until now, as much as I want to think about it as performance, I think it's still pretty much the artifact. Like the fabrication process does in every single project does have a kind of final stage, and I'm not really designing these objects for the process itself. I think in order to consider it a performance piece or even consider it a time-based installation piece, one would have to rethink the design process where you're not designing for the final state, but you're really designing, kind of approaching it more as a choreographer. And that is also something that I'm currently pursuing in my current research work, of like how do we move away from this idea of an architectural practice being about designing a thing that is static and just exists out there in space, but really designing a process or a choreography or even a responsive choreography. Like if we are thinking about buildings that respond to their occupants in a physical manner, what is that response and why is it meaningful to respond in that way?
Thank you, Maria. I don't see any further questions from the audience. If you have a pressing question, please raise your hand or type a question up pretty quick. I have one question for you, Maria. I was wondering, you're clearly in between so many different fields, and it takes a lot of expertise to be able to do what you're doing. So I'm wondering, what do you tell a prospective student? Like, what do they need to bring in order to work with you? Or how do you teach them individually? Like I can see a roboticist or a computer scientist certainly being not, I don't want to offend anyone, but maybe not as artistic and as creative as the other side of the spectrum.
I think, the students that I work with currently are mostly architecture students. And there's always like there are always students who are just excited from the beginning, who are like, oh, I didn't think this is part of an architectural practice. Turns out I can build robots. And it's like, yeah, you can, go for it. But I think generally with every student, the question is like to find something that they're really excited about and that they actually enjoy practicing. And I guess that was also the case with me when I was starting. I think it was two parts of me. One, that we just really enjoyed the process of designing, that it was not applied to, because I had all of these design skills and then suddenly realized that they can be useful in a very different context in designing these machines. And then on the other side, I was very naive in thinking that I can actually do as much as I think I can do. And I think that naivete was very, very productive. And that's also something that I try to encourage my students to pursue within reason. It's like, yeah, take risks, go for it, but also have a plan B, which I think is a very important moment.
Thank you so much, Maria, for joining us today and giving this very inspirational keynote lecture. I guess the audience can join me in just virtually clapping and applauding Maria. Unfortunately, we cannot do this and you cannot get all the energy from the audience right now. I'm very sorry. I hope we can see you in person sometime soon and reward you for this very great keynote.